Continuing the chi-square test. The last chi-square test that we have is a chi-square test of independence. We've done homogeneity chi-square test, and we've done goodness of fit chi-square test. Do you have any questions about those two types of tests? Right, they are the most straightforward. Remember, chi-square test of homogeneity assumes that everything is evenly distributed. A chi-square test of goodness of fit is testing the fit of the observed data to some theoretical distribution. So the most complicated chi-square test to do is the chi-square test for independence. This is what we do when we generally have what we call cross-classified data. So imagine that you work at the cafeteria and you're interested in whether or not people's opinion of the cafeteria changes over time. So you might survey first-year students, second-year students, third-year students, and fourth-year students on rating the cafeteria. And first-year students come in, and because they're enthusiastic about everything, because everything is new to them, they have really high ratings for the cafeteria, where 1 is worse and 5 is best. 70 of them rated the cafeteria 4 or 5. Very few ratings down in the 1, 2s, and 3s. But over time, what we see is this shift where by the time you're a senior, you're so sick and tired of the cafeteria, you can't stand going there, you give it really low marks. Even though the cafeteria hasn't changed at all during that time, your perception of the cafeteria has changed simply because of your experience of being here forever, and you just want to leave here and get on with your life and do whatever is next, buying good food at restaurants and things like this. So what a chi-square test for independence tests for is it tests to see if this distribution of the ratings is independent of the people who are being asked about these ratings. To what degree are the cafeteria ratings independent of where one is in their college career? And in this case, what we would see is that, because I made these data up, these have all the hallmarks of made-up data, you see that the opinion shifts over the 4 years, such that the cafeteria is rated less and less highly the further along you are in your career. So a significant chi-square test would find that this category is not independent of this category. And so that's what chi-square tests of independence test. In concept, that's what they do. So, like always, we're still going to calculate a chi-square test, where the chi-square is the observed minus the expected values squared divided by the expected, summed up, whoa, that's not a sigma, summed up across all of the categories that we have. But the trick with the chi-square test is, how do we go about constructing these expected frequencies? 40 and 30 is 70, and 30 is 100. So if we look at row totals here, each of these sums to 100. 40, 50, 60, 70, this sums to 70. 30, 60, 70, 80. This sums to 80. 70, 80, 90. This sums to 90. 70, 80, 90. And 40, 50, 60, 70. These are the column totals. There are 4 groups here, 100 in each row. These should both sum to 400. So if you sum down the row totals and sum across the column totals, both of these should add to 400. So let's check that for the column totals. 70 and 80 is 150. 90 and 90 is 180. And 70 is 400. So the grand total is 400. So the way we calculate expected values is very different for a chi-square test of independence. Because we're basing our expectation on the distribution of the data as it came to us to a certain degree. So for this cell here, the expected value is due to the influence of first-year opinions combined with the influence of cafeteria rating. The first-year experience is across all category ratings. The category rating 1 is across all 4 years. So the expected value for a rating of 1 for first years is the row total times the column total divided by the grand total. What's 7,000 divided by 400? Pardon? 17.5. So the expected value here, and I'll draw it in a different color, is 17.5. So you can see that the observation is slightly below what you would expect to see. In the same way, for this cell here, it would be 100 times 80 in this case, divided by 400. What's 8,000 divided by 400? That should be pretty easy. We get 4 by 80, that's 20, right? So here the expected value is an expected value of 20. We would do the same thing. Row times column divided by total would be the expected. Row times column divided by total would be the expected. Row times column would be the expected. And we would do that for this whole big box of numbers. So we would have observed, expected, observed, expected, observed, expected, observed, expected. In this case, this observed and expected would be this 100 times this 70 divided by 400. So this would be, because of the peculiarities of this table, because all of these are 100, these would all have the same expected values. And what you can see is that when you get to the 4th year, a much higher proportion of 4th year students are rating the cafeteria with its lowest possible rating than you would expect based on the overall ratings of 1 and the overall ratings of seniors. So that's a peculiarity because all of these row totals happen to be the same, and it's because I made them the same when I was making up this example. But that's how it works. But then once you have the observed and the expected values, calculating the chi-square is the same, except that in this case now you're going to have 20 different things that you're adding up. You're going to have 20 of these things that you add up to one another. So in this case, the degrees of freedom is the row times, is the row minus 1 times the column minus 1. So in this case, it would be 4 times 3. 4 minus 1 times 5 minus 1, which is 3 times 4, which is 12. So we would evaluate this by going to the chi-square table and looking up degrees of freedom 12. So we would have to have a value that was 21.026 or bigger in order to conclude that these things are not independent. So we're not going to work this one out. This is just to kind of show you how it works. We'll work on one where the row totals aren't so contrived. So this is a biological example. My apologies for non-biologists. But in this case, what we have is we have a situation where plants produce seeds. These seeds get distributed by animals. And then these seeds germinate and they become new plants in new places. But plants can also reproduce by breaking off parts of their bodies. And these new plants can then sprout new roots. These broken off pieces of plants can sprout new roots. And these roots take hold, and you get a new plant that way. This is called vegetative reproduction versus reproduction by seeds. And the thing of it is that different kinds of plants do this with different levels of success. But in addition to what plants do, animals interact with plants, and in some cases, animals eat seeds. They poop them out someplace else, and that's where the seeds then germinate. And this is how plants move around. Because they're rooted, they can't move themselves. So the way plants expand their ranges is by basically feeding their seeds to animals. Animals eat them, they go poop them out someplace else, and then now you have that plant in a new place. But you can also have plants breaking off, getting trapped in the fur of animals, and then being deposited later after the animal picks those plant parts off. So what they have here is two methods of plant dispersal, whether it's dispersal by ants or whether it's dispersal by vertebrates, things like, a coati or a deer or a skunk or a possum or a ronsoco. What's ronsoco? A capybara. So who does the dispersal of the plant? And then of those dispersal mechanisms, how many of these things are dispersing plants that regenerate only by seeds or can also regenerate by vegetative reproduction? And so what we have is this cross-classified table where 25 of the plants that were looked at in this survey are distributed by ants and only regenerate by seeds. Only 6 of these species are dispersed by vertebrates and produced by seeds. Only ants disperse 36 species that reproduce vegetatively, and vertebrates produce 21 species that reproduce vegetatively. So the totals are 61 species dispersed by ants, 27 species dispersed by vertebrates. 31 of these species regenerate only with seeds, but 57 of them regenerate with vegetative regeneration. So what you might expect is the most plants to be ant-dispersed vegetative reproducers because a lot of species are dispersed by ants and a lot of the total species are reproducing vegetatively. So you might expect this cell here to have the most observations because ants disperse a lot of plants and a lot of plants reproduce vegetatively. You might expect this to have the lowest one because vertebrates overall don't disperse very many plants, and seed only in terms of regeneration is also relatively uncommon. So you can see that the expectation of this cell is influenced by how many plants are dispersed by vertebrates versus how many plants only regenerate through seeds. And so that's why we calculate the expected values this way. So for this situation, what we would do for this cell is we would take the row times the column divided by the total. So that would be 31 times 61 divided by 88. And this would be what we would get for ant by seed only. For vertebrate by seed only, we would take not 6. We would take 31 times 27 divided by 88. For ant by vegetative, we would take 57 by 61 divided by 88. And for vertebrate by vegetative, we would have 57 by 27 divided by 88. Okay, so for each of these, we take row total times column total divided by the total, and that's what goes here. For this one, row divided by column, or row times column divided by total. For this one, row times column divided by total, and for this one, row times column divided by the total. Do the math real quick. And build yourself a table that kind of mirrors this table but has the expected values in it. Okay. All right, here's what I got. Let me know if you got the same. I got 21.49 essentially for this one. So if we're calculating the chi-square, what we would do is we would take 25 minus 21.4886364. We would square that difference, and then we would divide it by the expected value. And this would be this cell's contribution to the overall chi-squared analysis. I got 9.5113. Did you guys get this? I'm doing my math correctly. That would be squared, and we would divide it by the expected. Then we would have for this cell, I got an expected of 39.51. We would square that and divide it by the expected. And then for the last one, I got an expected of 17.4886. 364. That would be squared and divide by the expected. Before you do the calculations of the chi-square, look at these expected and observed and tell me whether or not you expect this to be a significant chi-square based on how far does this deviate from the expected? 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 Just looking at those things, would you expect this to be a significant chi-square or not as you add up all these differences? You're shaking your head no. Why not? They're all pretty close. And when you divide that difference, even though it's squared, when you divide it by the denominator, chances are those numbers are all going to be pretty small, which means that they're all going to add up to a relatively small chi-square value. So even before you do the calculations, you should already be predicting, in a sense, do I expect this chi-square to be significant or not, based on kind of what I see as the differences between the observed and the expected. A good guess would be, at this point, we expect the chi-square to be not significant, which would mean that these are independent of one another. The mode of dispersal doesn't have any effect on the kind of regeneration that the plants do, or another way of saying it would be the method by which the plants regenerate has nothing to do with the mode of dispersal. Calculate the final chi-square value and let me know what you find. Yeah.
And this comes off the table, right?
This comes out of, this came from the original data.
Oh.
Yeah. This is the observed minus the expected divided by the expected. Observed minus expected, observed minus expected. Yeah. That's why I wrote these down before I went to the next slide, so I would have them. Then these are the expecteds. Now note also, these expected values, if you add down, they sum to 61. These expected values sum to 27. These expected values sum to 31. And these expected values sum to 57. Once again, an internal check to make sure that you're doing your math correctly. Why are you not working? Work it. Work the problem. Oh. Oh, you don't have a calculator on your phone? Oh. Yeah, you should be able to. Yeah, you can do that there. Don't forget to always square the numerator. That's a mistake students sometimes make. Oh yeah, those numbers are all small, aren't they? Yep, it just all gets summed up.
So like once I calculate all these, I got these values.
Yep. Yep, that's what I got. I mean, that's what I recall that I got. I'll know in a minute. That's fine. It'll be close. But as I recall, that's pretty close to what I got. And that's pretty close to what other people are getting. Sorry, I'm looking over your shoulder as you work. It's got to be unnerving, I'm sure. You sat in the unfortunate spot that is right in front of where I'm oftentimes standing. What's that? It's weird. I'm not sure what exactly in here is front row. You're on the front row, but your back is turned to the board the whole time. All right. So here's the numbers that I got, and you'll see, once again, all these numbers are really pretty small. 0.5737, 1.29, 0.312, 0.705, and I got 2.88. So this is what we observed. Now, of course, what do we calculate? What do we compare this to? We compare this to the chi-square at an alpha level of 0.05. Remember what the alpha level is? The alpha level reflects how often you would say that these things are independent when in actuality they're not. Yeah?
How would it tell you that?
Oh, just assume that we're testing at 0.05 unless told otherwise. That's just kind of the standard thing. Usually if you were doing this for real and you were writing a paper or something, if you deviate from an alpha level of 0.05, you have to put some sort of justification in your methods as to why you're deviating from that. Whether you're deviating to make it more relaxed, which you have to have pretty good reasons for, or deviating to make it more stringent, which you generally have to have fewer good reasons for, but they still want to see why you were thinking that. So yeah, always 0.05. And in this case, the degrees of freedom is the row minus 1 times the column minus 1. In this case, there are 2 rows and 2 columns, so this is 1 times 1. So the degrees of freedom is simply a degree of freedom of 1. Where do we find that? We can go to a table. And we have a chi-square table at 1 degree of freedom and a 0.05. We have to have a chi-square value of 3.841 or higher in order to say that these things are not independent of one another. And so our hunch, when we looked at the observed differences between the observed and the expected, was that we would find that these things are actually independent of one another. And when we actually did the calculations, the chi-squared observed, in this case, is less than the chi-square in the table. Therefore, these things are independent of one another. Okay? That's how the chi-square test of independence works in terms of how you go about calculating it. Well, it just tells us that the dispersal mechanism here is independent of the method of regeneration of the plants. Ants are well-known seed dispersers. So the reason that somebody had this question in a biological sense is that ants are well-known seed dispersers. And so you might expect ants to primarily disperse plant seeds that are regenerating by seeds only. And so you might expect this cell in particular to be on the high side. But actually what we find is it's not that different than what we would expect based on the other kinds of dispersal that are going on in the other vegetative regeneration types. So what it's telling us is that this isn't related to this in any skewed sort of way. They're related just kind of how you would expect based on what's out there in the world. So they're independent of one another. If indeed this was really high, we would conclude that the dispersal mechanism is not independent of the way in which the plant regenerates. There are some plants, so this is just to once again give you some insight into the head of the person who did this study. There are some plants that they produce a seed, but then on the top of the seed or attached to the side of the seed, they attach a little ball and it appears white. I'm drawing it black just to set it off. There's a little tiny mint plant that grows. It actually grows on the side of the hill right behind Marston. If you go back there, go on in that space out there, you'll see a little mint plant with little tiny purple flowers, blooms in the spring and pretty much blooms throughout the summer. It produces tons of little tiny seeds. They're about this big. And when you look at each of those, there's this little white attachment to it. And that white attachment is filled with sugar. And what the plant has done over evolutionary time is it's evolved this mechanism by which it gives the ants an incentive to come and get those seeds. One year I was cleaning out the greenhouse here that's right behind White Science on the side that is also on where the back of Marston is. And I pulled up some flower pots, and underneath these flower pots was a colony of ants. And all throughout this ant colony were these seeds from this little mint plant. And a bunch of them were just the seed, but then there were some of them that were the seed with a little sugar packet attached to it. What the ants do is they grab the seed, they take it back to their colony. Once they're there, they eat the sugar packet off of it, and then they discard the seed. And so the plants have actually evolved a mechanism by which they coax ants into dispersing their seeds by giving them a little bit of an energy reward for doing this. These are technically called you don't have to know this is just useless information. They're called Myrmicophores, and it basically means food for ants. That's kind of the literal translation of it. And so there's a reason why you might think that plants are going out of their way to get them to disperse their seeds. You might expect ants to disperse more seed regenerating plants that can only regenerate through seeds, but it turns out that's not the case. Okay? So that's what that conclusion means to a biologist. How many of you are biologists? 2 of you. You don't give a shit about plants and ants, do you? No, you don't. But it's data. So let's talk about something other than biology. We're going to talk about healthcare. This is really, really old data. Really old data. And it looks at emergency room visits. And the question that the researchers asked was, how long ago was it when you had your last emergency room visit? Was it within the last 6 months? Was it within the last 7 to 12 months? Or has it been over a year since you've been to the emergency room? And they divided this up on the basis of income. How do you know this is really old data? These people are not making a lot of money. So this is, I think, data from the 1950s, if I remember recalling correctly. But the point of this is, does your income level have anything to do with how frequently or how recently you have been to the emergency room. If you go relatively frequently, chances are you've been there in the last 6 months. If you go less often, it's probably been 7 to 12 months. If you don't go very often at all, it's been in the last year. How many of you guys have been to the emergency room in the last 6 months? In the last 7 to 12 months? Okay. Well, do you mind telling us what it was for? You can also preserve your own health information. Oh, no, you had your appendix out. Oh, man, what was that like?
It didn't feel great.
I've heard that. The words I've generally heard to describe it are excruciating pain.
Yeah.
Yeah, well, good. I'm glad you survived. How many of you have been to the emergency room more than a year ago? Okay, so none of us are going to the emergency room particularly often. When you went to the emergency room, who paid your bill? Your parents. Your parents' insurance probably paid the bill. My insurance paid my bill to a certain degree. They don't ever pay everything. There's a copay and stuff like that. And the copay for emergency room visits is relatively expensive. If you just go to if you have an emergency, like sticking your finger into a router blade while you're making a pill box, like I did, which was my last emergency room visit, your eyes are wide. Do you know what I mean by that? Yeah, a router is have I told you about routers? Yeah, a router is a little thing. It spins a sharp blade at like 6,000 RPMs, and you use it to trim the edges off of wood and to shape the edges of wood. And I was pushing a pillbox through it, and the router grabbed the pillbox, shot it out, and the hand that I was pushing the wood up against the fence of the router because it was pushing against the wood, when the wood shot out, my finger went into the router, and I chopped up the tip of my middle finger. And yeah, it wasn't happy, but at the same time, I could have gone to my regular doctor and gotten him to look at it, but they weren't available, and so I went to the emergency room, and it was kind of expensive. The copay for emergency room visits, I think, on my insurance is like $100. So that was a $100 mistake, just at the get-go, not counting antibiotics and the tetanus shot and everything else that I got. So it's expensive to go to the emergency room, which is why people don't go as often as they might, because the copays are relatively expensive. So the question is your frequenting of the emergency visit influenced or related to how much money you have available? And so this is the kind of socioeconomic data that somebody would want to know about. Do you already see some patterns? Yeah, what are the patterns that you see? Yeah, generally it seems like if you have more income, there are more visits. So there's a patterning across the rows, a general increase in visits as income increases. Is there patterning to the frequency? Yeah, not only do people with more money go more, but they also have been more recently than other people. But also within this row, even poor people have been there relatively recently relative to the number of people with low income. So the question is this patterning that we kind of see in this table, is it statistically significant? Now, how do we do this? Well, the first thing we have to do is we have to calculate the expected values. So we would take the row total times the column total and divide it by the grand total, and that would be the expected value for this cell. Now, this involves a lot of hand calculations at this point, right? Because we have 1, 2, 3 by 1, 2, 3, 4, 5. We have 15 different expected values to calculate, et cetera, et cetera. So let's save ourselves a little bit of trouble. Pull up your favored spreadsheet program. Doesn't matter if it's Excel or if it's something else. Just pull it up. I'm going to do mine in Excel. That's where I do most of my work. And just right now, input the base table. So you should have something that looks kind of like this. Can you guys see that? No, you can't see that. Why can you not see that? There we go. When you get the base table, I didn't bring sticky notes today, but when you get the base table entered in, just lean back in your chair like you're relaxing because you've done your job, and we'll proceed on after that. So in answer to the question bopping around in some of your heads, on the next homework assignment, will I allow you to do things in Excel? Yes, I will. I'll also require you to do some things by hand, but I will allow you to do some things via Excel. Everybody have the base table in? Anybody not have the base table in? Okay, so to calculate the expected values, well, what do? Let's just write an equation in Excel, and let's write the most flexible equation that we can. So what we want to do is for this first column, which is 6 months, I don't know why I have months instead of months. So right here, we want the expected value, and the expected value is simply going to be the row total times the column total divided by the grand total. And so we could certainly write the equation this way using column references, but it might be better to do this with references that don't change as we copy. So what we want to do is we want to calculate this for E3, E4, E5, E6, and E7. So what we can do, at least in Excel, is we can put a $ in front of the B and the 8, and a dollar sign in front of the E and the 8. And what that does when you do that, dollar sign. What that does is it makes this a fixed reference. This is a fixed reference to this cell. This is a fixed reference to this cell, and it won't change as you drag down after you have done this. So if we do this correctly, it should give us that. Then we can just grab this formula and drag it down. And what it is doing, if you check it, it's changed the row total that we're using, but it hasn't changed the column total and the grand total. And when you sum this, it should sum to 1640. Once again, if we've done our math correctly. Yes, ma'am. I can. Yep. I'll actually write it on the board. The first equation is E3, which is the eth column, the third row, times dollar sign B8, dollar sign B, dollar sign 8, divided by dollar sign E8, E dollar sign 8. And once again, that will allow you to vary this cell as you drag down, but it'll keep these cells the same. Okay? Everybody accomplish that correctly? All right, cool. We're going to do the same thing for the next column, but in this case, it's going to be equal to, once again, this row, but now it's going to be times the other column total, and we'll go ahead and put dollar signs in front of the C and the 8 there, and then we're going to divide it by the same grand total, which you can put in the cell, or you can just type in 2764. Doesn't really matter. It'll do all the same thing. And when you then copy that down, once again, that column should sum to 567. So here, so I've done the same formula. I've just put in numbers instead of the cell references. And then for the last column, you can do equal, and in this case, this is the cell number, but you can also just do times 557, which is the column total, divided by 2764. 2764. And once again, I've just replaced the numbers as constants instead of using the references, but once again, that should add to 557 in this case. So 3 different ways: replacing the cell references with numbers except for the one cell that is variable, replacing one of the numbers, the grand total, and using cell references for everything else, or using cell references for everything. Doesn't really matter how you do it, as long as you get the right answer. Let's just sum these rows to make sure that we've done our math correctly. 259, 326, 375, 607, 1197. So we ultimately have the same number of expected observations as we have observed observations. All right, everybody with me? You guys all getting same stuff? All right, so now we have to calculate the chi-square. Well, what is the chi-square? Well, the chi-square is equal to, and now give yourself two parentheses here, because what we have to do is we have to do the observed, which in this case is 186, minus the expected, which is 153.675, but then we have to square that. So use the caret symbol, and, oh no, I didn't. I hit a wrong button. So use the caret symbol, and then we want to enclose all of that in parentheses and then divide by, once again, the expected, which is 153.67. In this case, you want to use cell references for everything, and you want to not make any of them fixed. Okay, so this is the observed minus the expected, then square it, then divide by the expected. So in this case, where I've put it, because I've put it down here in row 13, it is, well, it doesn't matter where I put it. This is in row row 3, B and H. So it's B3 minus H3. Close that parentheses, raise it to the square, close that parentheses, and then divide it by the expected, which is H3. So this is my equation based on my cell references in my spreadsheet. The reason you have two parentheses out here is you want to do this subtraction, then you want to square it, but you want to divide that whole thing by H3. If you didn't have two parentheses, it would divide this 2 by H3, and that's not the power that you want to raise it to. So whenever you're working on formulas, either in Excel or in R, always remember your order of operations. Please excuse my dear Aunt Sally. Parentheses first, then exponents, then multiplication and division, and then addition, subtraction. Whoa, can't spell. So we put this in parentheses so it doesn't do anything else with it. So we put this in parentheses because it's going to be doing division after it does exponents. So you just have to use parentheses to make sure it's doing things in the right order. You guys get 6.799 for that?
Yep.
Now at this point, life is easy. You can do this, you can drag this over, it'll autofill, and you can drag it down and it will autofill. So when you check this formula over here, this should be 35 minus 52 squared divided by 52. And in Excel, it color codes everything so you can keep track of which cells are which. That is each cell's contribution to the overall chi-square. So you can now just write yourself a sum, and you can just sum across this whole table. And this is the chi-square value. Way faster than what you did a few minutes ago on a much smaller table. So in this case, we have a chi-square value observed of 35.6316.462. What is the chi-squared that we need to go and look up in the table?
How
Yeah.
did you do the chi-square again? Because I just summed the entire thing.
You got 47. Oh, did I forget a row? Oh, I did forget that row. All right, sorry. 47.89, is that what you guys got? All right. All right. So how do we find out the chi-square value that we need to look up in the table? We need to check at an alpha level of what? 0.05. And what will be our degrees of freedom in this case? It's rows minus 1 times columns minus 1, right? We have 1, 2, 3, 4, 5. We have 5 rows and 3 columns. So this is 4 times 2. So our degrees of freedom equals 8. So we can go back to our chi-square table. And find degrees of freedom is 8, 15.507. Okay. Because the observed value is way bigger than the tabled value, we would conclude that these things are not independent of one another. So, emergency room visits really frequency of emergency room visits or recency of emergency room visits Now, we can kind of figure out what's going on in the data by looking at the differences between the observed versus expected as expressed by the contribution of each individual cell to the chi-square value. So let me go to that. In your PowerPoint, I've got the raw data, then I've got all of the expected values, then I've got the chi-square contributions, and the total chi-square. But what you see here is that some of these cells contribute a lot to the chi-square value. Others of these cells contribute almost nothing to the chi-square value. And then some of these contribute more to the chi-square value. So the cells that are contributing heavily to the chi-square value are low-income rows, and this highest income row is contributing the most to the significance of the chi-square value. But just looking at the contribution to the chi-square value doesn't tell you anything about the direction of this. Is this contributing because these people go to the emergency room more or less than they're expected to? So while this tells you which cells to pay attention to, it doesn't tell you the direction of the change. So one of the things that I like about doing this in Excel is that when we go and look at Excel, we can actually see this is lower than you would expect. This is higher than you would expect. And this is higher than you would expect. Oh, it's not showing up on screen. Sorry. This cell here is, I'm sorry. This cell here is lower than you expect, higher than you would expect, and then this one is higher than you would expect. This one is lower than you would expect, higher than you would expect, higher than you would expect. So in each of these cases, now I've totally messed myself up. I don't know how the school feels about me writing on LCD screens, but I guess I don't really care. This is lower than you expect, higher than you would expect, higher than you would expect, lower than you would expect, higher than you would expect, higher than you would expect. Sorry. Got that just opposite. This is higher than the expected, lower than expected, lower, higher, lower, and lower. This is lower than you would expect. This is higher than you would expect. And this is higher than you would expect. This is, let's see, those were all relatively low. So it's these two. Yeah, okay. So those are kind of where the big differences were, the big contribution to the overall chi-square. And what it basically indicates is that people with less money have been to the emergency room more frequently, more recently, and less frequently further back in the past, whereas people with more money have been to the emergency room less recently than you would expect, but it's been longer since they've been to the emergency room. And so it might be that some people are more likely to injure themselves needing to be taken to the emergency room, which is why this frequency is higher than you would expect, as opposed to these people who may have white-collar jobs, as a result don't get hurt as much, therefore they haven't been to the emergency room as much most recently, but they've been more in the more distant past. So this is how you then tease what this thing means. This thing means something. It's telling you that there's some pattern to this contingency table. There's some pattern to this cross-classified data. But just looking at that number doesn't tell you what specifically in the data you should be paying attention to. To do that, you have to look at which of these cells is contributing heavily to this value being significant. And then you have to go back and say, okay, these are the parts of the data that are contributing a lot to the chi-square. What are those specific cells telling me? And interpret it by looking at how does the observed compare to the expected? There's more observed than you would expect. Okay, so why might that be the case? Especially because it's so consistent here. The reason that these things aren't independent is because for some socioeconomic groups, there's more than expected in the minus 6 months category and less than expected for another group in the less than 6 months category. That's where the lack of independence comes from. Things moving in one direction in one part of the table, moving in the other direction in other parts of the table. Chi-square test for independence. The reason it's more complicated than the other two chi-square tests is because the method of calculating the expected values is different. But other than that, once you have those expected values, calculating the actual chi-square value is exactly the same. Observed minus expected, square it, divide it by the expected, add it all up. Okay? Questions? All right, on Wednesday we will cover Shapiro-Wilks test, which is a test for normality. I will see you then. What? I need to post a homework for this material. Yep. It's not posted yet, but I will get it up soon enough. Oops, sorry.